Hello everyone and welcome to episode 4, Raster Calculations in R. So again, I'm starting with a new RStudio session. My console is over here. My environment pane is empty because it's a new RStudio session. And we see that my R projects folder has already been opened and it's here in my main folder. The previous 3 episodes are here as well, as is the data folder where our rasters live. So I'm going to go ahead and open up a new script. Again, you can continue working with the same script you had been working with before. In that case, you won't need to reload some of the data sets and packages, but we're going to go ahead and start anew here. So I'm going to go to File, New File, our script. Again, Untitled 1, which we're going to go ahead and just save. So I press Control S. I'm going to call it Episode 4. Raster Calculations, and save that. We can see now episode 4 Raster Calculations is in my folder here, in my Geospatial carp folder. And we see here that the title of the R script has updated as well. So let's input some more information. So this is going to be episode 4. Raster Calculations in R, my name, let's do the year. So in this episode, we're going to ask the question of how do I subtract one raster from another and extract pixel values for defined locations. So our objectives for this lesson are to perform a subtraction between 2 rasters using raster math. And we want to perform a more efficient subtraction between 2 rasters. We're going to learn the overlay function from the raster package. And we're also at the very end going to show you how to export a raster as a GeoTIFF file. So some key points are that rasters can be computed using mathematical functions. The overlay function will provide an efficient way to do raster math. And the write raster function will be used to write raster data to a file, to a GeoTIFF file. All right, so with that, let's go ahead and load in our libraries. So we're going to load in the raster library, the rgdal library, the ggplot2 library, and dplyr. Just going to go ahead and highlight all 4 of these, press Control Enter to run all 4 lines at once. So again, we have some red messages. Again, these are messages, but these are not errors. So everything looks good. All right, so in this lesson, we're going to be using the harv dsm crop.tiff and harv dtm crop.tiff raster files. We will also be using the SJER, that's the San Joaquin experimental range, both the DSM and DTM files for San Joaquin. So again, if you are continuing to work from the same script that you had been working with previously, then you don't need to go ahead and reload all of these raster files, but we are going to go ahead and do that here. So let's say load in rasters. So I'm going to go ahead and create dsm_harv using the raster function, double quotes, navigate to my data folder, my raster subfolder, harv_dsm crop.tiff. I'm going to go ahead and run that. So now again, we have that dsm_harv object as a raster layer in my environment. Let's go ahead and just convert that to a data frame right away. dsm_harv_df as.data.frame, open parentheses, dsm_harv object, and then the argument xy equals true. Remember, we have to convert our rasters to data frames in order to plot them and to use ggplot. All right, so maybe I'll add some more comments. So this is harv DSM. Now let's do the same thing for harv DTM. So that's going to be DTM underscore harv raster double parentheses double quotes data raster harv underscore DTM. Looks like we have two DTM files. I'm going to go ahead and pick the first one. Oops, Control Enter. And let's go ahead and make that a data frame right away as well. So that'll be DTM underscore harv underscore DF as dot data dot frame, open parentheses, DTM underscore harv, argument XY equals true. Great. All right, so let's go ahead and do this all for the SJER, or the San Joaquin experimental range as well. So this will be SJER and we'll do this for the DSM data. So this will be DSM underscore SJER, raster, open parentheses, data, raster, and that'll be SJER underscore DSM. Again, we have multiple options. We pick the first one, that's SJER underscore DSM crop.tiff. And let's go ahead and make that into a data frame. SJER underscore DF as dot data, data dot frame, open parentheses, DSM SJER is the raster, and we specify the argument XY equals true. Then let's go ahead, and I think this should be the last one. Let's do this for SJER, the San Joaquin experimental range, for DTM. So this will be DTM underscore SJER, raster function, open parentheses, double quotes, data raster SJER underscore DTM crop.tiff. Again, we have several options there. We pick the underscore DTM crop.tiff. And let's make our final data frame here. So that'll be SJER, or DTM underscore SJER underscore DF as dot data dot frame, open parentheses, DTM underscore SJER, argument XY equals true, and press Control Enter. And we have our last data frame here. So all of these data frames look like they have quite a few observations. So that immediately tells me that some of these plots will take a while to load, so just be prepared. If it doesn't error out, just let it keep running for a while. All right, so to set the scene a little bit, we often want to combine values and perform calculations on rasters in order to create a new output raster. So this episode is going to cover how to subtract one raster from another using basic raster math. Specifically, we're going to show you how to do raster math two different ways, and to show you and to illustrate using the overlay function, which is generally more efficient. This episode will also cover how to extract pixel values from a set of locations, for example, a buffer region around a plot, locations at a specific field site. So with that, let's dive in. In this next section, let's call it raster calculations in R. So let's say, for example, we are interested in mapping the heights of trees across an entire field site, and we might want to calculate the difference between the digital surface model, or DSM, and the digital terrain model, or DTM. The resulting dataset is referred to as a canopy height model, or CHM, and represents the actual height of trees, buildings, etc., with the influence of ground elevation removed. So to learn a little bit more about DSM, DTM, and CHM, there's a lot of excellent sites that are linked to the site here, to the carpentry site here. provided by NEON, or the National Ecological Observatory Network. So if you want to learn more, I would recommend you go to those links as well. So first things first, let's learn about 2 ways to perform raster calculations. So we can calculate the difference between 2 rasters in 2 different ways. The first one is by directly subtracting the 2 rasters in R using raster math, or for more efficient processing, particularly if our rasters are large or the calculations we are performing are complex, we can use the overlay function from the raster package. So let's show an example of some raster math. So remember, CHM, or the canopy height model, is the surface model minus the terrain model, right? So we can create CHM underscore harv, and that should be equal to DSM underscore harv minus DTM underscore harv. So if I press Control Enter, we see that now CHM underscore harv is a large raster layer. So it looks like it worked, but to be sure, let's go ahead and plot it. So recall, if we want to use ggplot for plotting our rasters, we have to first convert this into a data frame. So let's create CHM underscore harv underscore df as .data.frame, open parentheses, CHM underscore harv, comma, xy equals true. All right, so now we are told that CHM underscore harv underscore df is a data frame, and it has 968,044 observations with 3 variables. Okay, so that makes sense. Makes sense because DSM and DTM had the same number of observations, so that's promising. So let's go ahead and plot it. So we use the ggplot function, open parentheses, plus gm underscore raster, open parentheses, data equals CHM underscore harv underscore df. Let me move this down just a little bit. Plus, oh, pardon me, not plus. Let's go inside that parenthesis there, add a comma, AES aesthetics, open parentheses, x is equal to x inside AES, and then y is equal to y, and we specify fill is equal to layer. Now I want to just pause here and explain how I knew that fill is equal to layer. So if I go down into my console and I use the structure str function, and I look at that new data frame we created, CHM underscore harv underscore df, I can see that the default variable name that is given to my data frame is layer. So this is what I want the values to be filled in with. All right, so then I add plus. I want to add some colors to this. So scale underscore fill underscore gradient n, open parentheses. I'm going to give this legend a name, canopy height, in double quotes. And then to specify colors is equal to terrain.colors, and I want to give this 10 colors. And lastly, but not least, we want to add chord underscore quickmap, open parentheses, and press Control Enter. And we have our canopy height model. So this looks great. This is certainly one way to do this. Let's look into this in a little more detail, though. Let's look at a histogram of this canopy height. So let's add a histogram. Let's make histogramming a verb. All right, so ggplot, open parentheses, data is equal to CHM underscore harv underscore df plus, and I'm going to use the geom underscore histogram, open parentheses. I'm going to specify aesthetics, AES, is equal to layer. And let's just press Control Enter and see what we get here. So we get a warning, it's not an error. And we have our counts. We have the counts of canopy height, so that's our layer. And we can see that it looks like there's quite a few observations that have zeros. Maybe this distribution is a little left skewed outside of that. Looks like there's quite a few observations that are sort of at about, let's say, I don't know, 23, 22. And it sort of drops off, those observations sort of drop off right up until 30. And looks like 30 is the largest canopy height that we have. Although, to be certain, let's go ahead and apply the summary function. So summary, CHM underscore harv underscore df. I'm going to select layer, press Control Enter. And in fact, it looks like our maximum value is 38.17. So we must have at least one observation that's somewhere around here. All right, so we've now seen how we can do simple raster calculations using two rasters, and the same standard math operators seem to work here, and how we convert that resultant raster into a data frame. And then we plot that data frame, and we can apply summaries and histograms and other exploratory tools to that resultant raster layer. So with that, we are ready for our first challenge. All right, so challenge number 1, explore CHM raster values. It's often a good idea to explore the range of values in a raster dataset, just like we might explore a dataset that we collected in the field. So there's 4 tasks to this challenge. Number 1, what is the minimum and maximum value for the Harvard Forest Canopy Height Model, or CHM underscore harv, that we just created? So I may have given you some hints there, but see if you can find another way to do that, to find the minimum and maximum values. What are the 2 ways you can check this range of data for CHM underscore harv? Number 3, plot a histogram with 6 bins instead of the default and change the color of the histogram. And finally, number 4, plot the CHM underscore harv raster using breaks that make sense for the data. Include an appropriate color palette for the data, and plot the title, no axes, ticks, and labels. All right, so let's go ahead and go over our challenge number 1 solutions. Let's scroll this down just a little bit. All right, so number 1, I wanted you to find the minimum and maximum values for the CHM underscore harv. So I already showed you one way to do this, right? So it looks like we can apply our summary function to the data frame and then specify the variable layer. And we can see that the minimum value is 0 and the maximum value is 38.17. But let's see if we can do this a different way, min max values. So let's try using the min function. So min CHM underscore harv, money sign layer, and press Control Enter. All right, so it looks like the answer is 0, which confirms what we saw from the summary. And lastly, let's use the max of CHM underscore harv underscore df, money sign layer, Control Enter. And we see further out to, the decimals are kind of further out than we had before, but the maximum is also 38.17 here. So there's probably other ways to do this as well. But again, in R, there's multiple ways to get the same task done. All right, so number 2, we wanted you to create a histogram, right? So let's go ahead and do that. So first things first is I want to go ahead and use ggplot, open parentheses, and in here I want to specify data is equal to chm underscore harv underscore df plus geom underscore histogram AES aesthetics, open parentheses, layer, comma, color is equal to black, comma, fill is equal to, I'm going to specify dark green, and bins is equal to 6. So let's see what happens when we do this. Control Enter. Alright, so here we have 6 evenly spaced bins. So it looks like it's somewhere between, I don't know, 0, 10, 20 or so. Not certain. But it looks like these bins, so when we specify the argument, comma bins is equal to a number, the bin size is going to be the same throughout the entire histogram, right? However, for number 4, we want to create custom bins, right? So I apologize, this should actually be number 3, this is number 4, and number 2 we talked through different ways. Alright, so for number 4, we wanted you to create custom bins, right, that were sort of scientifically driven. So I created some custom bins, created a vector of custom bins, and I have them at 0, 10, 20, 30, and 40. So we can see now that I have this vector here, custom bins, 0, 10, 20, 30, 40. And now I'm going to use ggplot, open parentheses, plus geom underscore raster, open parentheses, data is equal to chm underscore harv underscore df, AES aesthetics, open parentheses, x is equal to x, y is equal to y, comma, fill. Now instead of filling in the same color here, so I did dark green above here, I want the fill to actually be equal to something different. So what I really want this fill to be is I want it to have a separate color for each of those breaks that I created, those custom bins, right? But I don't have that observation yet in chm underscore harv underscore df, right? So again, if I look at the structure of chm underscore harv underscore df, I don't have anything that would tell me what those breakpoints should be, right? So before I get to my ggplot, I actually have to go ahead and create a new variable. So let's go ahead and create a new variable for custom bins in data frame. All right, so we're going to amend our chm underscore harv underscore df data frame. And the input data frame is going to be the same, we're just amending it. We use our pipe operator from the dplyr package. And we're going to use this mutate function. And we're going to create a variable called canopy underscore discrete. And it's going to be equal to cutting that layer variable into a number of breaks, which is going to correspond to those custom bins. So let's go ahead and run that. And then let's take a look at what we get. So let's look at the structure of chm underscore harv underscore df. Control Enter. So now we can see that I have this new variable here, right? Canopy underscore discrete. Now let's take a look at the levels of canopy underscore discrete. So levels, chm underscore harv underscore df, money sign. canopy discrete. And we can see that the levels are 0 through 10, 10 through 20, 20 through 30, and 30 through 40. All right, so that looks good. So now this canopy discrete is what I want my fill to be, canopy underscore discrete. Plus scale underscore fill underscore manual. I want to add values equal to terrain colors, and now I'm going to add 4 terrain colors. And recall we need our chord underscore quick map, open parentheses. So then I press Control Enter. Wait for a second because these plots all take quite a bit of time. All right, and we finally have our plot here. So we have our X and Y coordinates. We have our canopy colors, 0 through 10, 10 through 20, 20 through 30, 30 through 40. And it looks like we actually have this NA category, right? That happens to be the same color as 30 through 40 because we only specified 4 terrain colors, but there was actually another hidden group that we weren't aware of. And this corresponds to this warning message that there are actually 8,914 rows that were NAs. And so the NAs right now are the same color as that 30 to 40 range. So this is helpful to bear in mind that we should always explore our data more fully. Notice here, when I looked at levels, I wasn't told that there were NA values, right? If I do table, open parentheses of CHM underscore harp underscore DF, money sign, canopy discrete. I also am not told that there are any NA values. How could I find out then if there are any NA values? So we can use this function. Let's do table, open parentheses, is.na, CHM, underscore harp underscore DF, money sign, canopy discrete, Control Enter. And here we see a table that there are 959,130 values, and then we see that there are in fact 8,914 NA values. So just things to bear in mind. All right. So next, let's go ahead and learn about the overlay function. All right. So raster math, just like we did, right, subtracting the terrain from the surface model, is an appropriate approach to raster calculations if 2 conditions hold. So if the rasters we are using are small in size, and if the calculations we are performing are simple, so then we can use simple operators, minus, plus, divide. However, raster math is less efficient approach if the computation becomes more complex or if the file sizes become larger. So in these instances, the overlay function from the raster package is more efficient. Specifically, again, in cases when rasters we are using are larger in size, when the rasters are stored as individual files, when the computations performed are complex. So just to give you a brief idea, I'm going to sketch out the sort of, I guess, skeleton of the overlay package. So there's going to be some output raster, our assignment operator, and then this overlay function, open parentheses, is going to be the first raster, the second raster, and then fun stands for function, so then function name. So a function would be an example, like divide, multiply, square root, some sort of mathematical function, right? All right, so let's go ahead and explore this overlay function with our harv data. So we're going to create an object called CHM underscore ov underscore harv. So O stands for overlay. Assignment operator, this overlay function, open parentheses. So the first raster is DSM underscore harv. The second raster is DTM underscore harv. And the function we're going to write out, so it's going to be R1, raster 1, raster 2 for the arguments. And the function is just going to return R1 minus R2. So I know this will work because if I look at the help for overlay, so question mark overlay, we can see that the arguments are, the first is raster 1, or x, the second is raster 2, or y, and so then this function is taking in the first raster and the second raster, and then this is what it's returning. So let's take a look at it. So I press Control Enter. And it looks like everything worked. So we have indeed a large raster, 968,044 elements. All right, so now we are ready to create a ggplot. All right, so again, we have a raster and we want to create a data frame. So we're going to create CHM ov underscore harv underscore df. We use the function as.data.frame, open parentheses, CHM underscore ov underscore harv, and then the argument xy equals true, and press Control Enter. So again, we see here in the data frame, we have 968,044 observations. So that looks good. So let's go ahead and plot that. So that's ggplot, open parentheses, plus gm underscore raster, open parentheses, data is equal to the CHM underscore ov underscore harv underscore df, plus, oh, pardon me, not plus. Let's go back inside those parentheses, add a comma, AES aesthetics, x is equal to x, y is equal to y, fill is equal to layer. Again, I know that layer is the variable of interest because I can always go to my data frame and indeed confirm that the values that we want to plot are called layer. All right, now we want to add some color, so that's scale underscore fill underscore gradient n, open parentheses. Inside here, we give our legend a name, canopy height, comma, colors is equal to, I'm going to add 10 terrain colors, 10. And of course, lest we forget, chord underscore quick map. All right. And here we have our plot, our canopy height model. All right, so now we've explored two different ways to do raster calculations. We've explored different ways to plot those calculations. Let's say we create a raster based on this subtraction. We have this canopy height model, and we want to save it. We don't want to keep recreating it every time. So there are also ways in R to export a GeoTIFF file. And with this, we will use the function write raster, also from the raster package. All right, so let's give it a try. So it's the function write raster. Notice that we don't have anything on the left-hand side because we're not assigning the output to anything at this point. We're writing the raster, and we're going to specify the file name and location of where we're going to add that raster to. So we're going to add CHM, write raster CHM underscore ov underscore harv. We're going to call it, we're going to specify file name is equal. Now I'm going to go ahead and put it in my data folder. And I'm going to call it CHM underscore harv dot tiff. You can also save it into our immediate geospatial carp directory here by excluding this. But for me, I'm going to go ahead and put it in this overall folder. Another great practice would be maybe to have another subfolder here called modified data or updated data, but for now we'll just go ahead and put it in the data folder. So let's just go back up to our main directory so we know where we are. So that's data \CHM underscore harv.tiff, comma, I specify format is equal to, in double quotes, GTIFF, where G and T are capitalized, comma, overwrite equals true. Now I add overwrite equals true so that every time I run the script, it will overwrite that raster file and it won't give me an error. The error it would otherwise give me would say something like, this file already exists, so it cannot be overwritten. In our case, we do want to overwrite it in case there's something there already. And we specify this argument NA flag equals -9999. So that's the flag for any NA values, which we did observe there were some. Instead of having NAs or missing, we're going to add, it's going to be this very large and scientifically improbable number. All right, so everything looks good. Let's go ahead and press Control Enter. We don't have to highlight everything. You can and run it. Your cursor just has to be somewhere on the line. So let's go ahead and press Control Enter. Again, this is taking a second because it's a fairly large raster. And we get this warning. Again, this warning will be fine. And if we go to data, we see that indeed the CHM underscore har.tiff exists in our data folder. So if we want to double check to see that we in fact did do everything correctly, let's load it in. Gem o har to make sure. So let's call it, I'm just going to call this double check. We use the raster function, double quotes, go into data, \, going to go ahead and load this guy in. Now let's plot it. Let's do things right. So let's go ahead and create this as a data frame. So let's call it double check underscore df as .data.frame, open parentheses, double check, xy equals true. All right, and let's do a quick ggplot. So ggplot, open parentheses, gm underscore raster, open parentheses, data is equal to this double check df, AES, open parentheses, x is equal to x, y is equal to y. Now I'm not sure what fill should be, so I'm going to start fill and go, ooh, I'm not actually sure what it is in the data frame. I jump down to my console, again look at the structure of my data frame, that's str, open parentheses of double check underscore df, looks like it's called CHM underscore harv. And to make sure things kind of line up, let's do scale underscore fill underscore gradient n, open parentheses, name is equal to canopy height, colors is equal to terrain dot colors 10 plus again chord underscore quick map. Let's go ahead and run that. And indeed, we get the same raster. So it looks like our right raster did work. All right, so with that, we are ready for our second challenge. So we've been working with the Harvard rasters, and now I want you to switch to working with the San Joaquin experimental range. So import the SJER, the San Joaquin experimental range, DSM, so that's digital surface model, and DTM, digital terrain model, raster files, and create a canopy height model. Again, recall, canopy height is equal to DSM minus DTM. Compare the two sites. You should have the DSM and DTM data for the SJER site already loaded. Don't forget to check the CRSs and units of the data to make sure that everything lines up. Alright, so the two tasks are to create a CHM from the two raster layers and to check to make sure the data are what you expect, and to plot the CHM from the SJER, or the San Joaquin experimental range. All right, let's go over our challenge number 2, solutions. Let's move this down a little bit. All right. So I'm going to go ahead and create CHM underscore O underscore SJER, and I'm going to use the overlay function. I think you could have also done this by just subtracting the two rasters, but for good practice, DSM underscore SJER, comma, DTM underscore SJER, comma, fun is equal to function, open parentheses, raster 1, raster 2, and then I want to return R1 minus R2. All right, and I run this. All right, looks like it worked. Let's go ahead and convert this to data frame. So it's going to be CHM underscore OV underscore SJER underscore DF as dot data dot frame, open parentheses. We put the resultant raster over as the first argument, this one, for San Joaquin experimental range. We specify the argument xy equals true, control enter. All right, so let's create a plot of this new CHM for the San Joaquin experimental range, and I'm going to go ahead and just create a histogram. Just playing around and exploring the data a little bit. So that's ggplot, open parentheses, data is equal to CHM, this OV SJR underscore DF, plus we use the geom underscore histogram. We specify AES is equal, now I'm going to double check again, so let's look, STR, CHM, OV SJER DF, pardon me, and in fact that variable is layer, so we specify layer again, and press control enter. All right, wow, we have a lot of zeros here, right? You can see there's a lot of zeros. The fact that the x-axis goes all the way up over here tells me that there's at least one observation out here, but it looks like most of these values are 0 for the San Joaquin experimental range. What you could also do a custom bin, so create custom bins if you wanted to look at this data in a little more detail as well. I'm going to go ahead and skip to creating a plot of the CHM. So that's ggplot, open parentheses, plus geom underscore raster, data is equal to CHM ov SJER DF, comma, AES for aesthetics, x is equal to x, y is equal to y, fill is equal to layer in this case, plus scale underscore fill underscore gradient n. Name for our legend is canopy height, comma, colors is equal to terrain.colors. I'm going to give it 10 colors again. And then plus chord quick map, right? Chord underscore quick map. Just move this down a little bit. All right, let's get ready for a final plot. Control Enter. And here we have our canopy height for the San Joaquin experimental range. Recall from our histogram, there were very few values that were above 20, and we can see that reflected in the raster here. Most values were 0 or just around 0, and we can see that here as well. Most of this raster appears to be at or near 0. So with that, we have now learned how to create raster calculations using R, Control Save, and we have also learned a little more detail into plotting. So with that, let us know if you have any questions. Thank you.